Okay. I've got 5:02, so I'm not really too late in recording, and you may notice the room here a little bit backlit. It's I'm at my son's house in Colorado Springs now, and hopefully all of you are staying safe. Uh, uh, Although you kind of wish you were in New Zealand or Australia or someplace where things are not so bad right now. Let's see. Guess we can share the screen. Share. Okay. And can I? Does this let me? Show the grid view and get a grid view up and see more of you here. All right. Think that lets me see everybody, and I've got the attendance list, and I'm in draw mode. So Joe Blackrow is here, I see, and Kimmy Mila is not. Felicia, I see, is here. I don't see Ryan yet. And Jermaine is here. Terry Haskell up in the corner there. Let's see. Eleanor, haven't seen her.
Over there.
Right. We have Janice is there, sort of spinning around a little. Yeah, trying to figure out where to put the camera isn't always the easiest thing. Let's see, is Brad here? Don't see Brad. Oh, chat message. I'm here, Tiff King. Okay. Yeah, all right. There we go. Tiff King is here. Megan is here. Only got one Megan's. Joni Morissette. Doesn't look like she's managed to show up here on time. Christina Payne. Tony is here. And we have two Victorias, so I should mark you both here. Okay.
Yep, Victoria's here. Victoria Pino.
Okay. All right. Got you both. Let's see. Brittany. She sent me a couple of emails today. I think she's probably trying to keep up with the. Was that Brittany? No, it was somebody else. I'm sorry. Who we got? I'm also here, Victoria Phelps. Yeah. Okay. Yeah, maybe you can't see it, but I have checked you off there on the side. Of course, I don't know how quick those chats pop up. I really don't. I and Samantha, don't see her yet, and some others. Shah is here. Shah was here. Yeah, Shah is here. And Justice hasn't made it, nor Sherry. Okay. Let's file, save those. Okay. And you go back to the select point and home, and I guess I can share the screen and go to the PowerPoint, and that would just leave me with a overlap. Yeah, slideshow from the beginning. Oh, yeah, I don't know what you guys are seeing here. Guess I can minimize that. And that's where we are now. We have social science 313 and straightforward statistics, and you got a chime. Somebody new is here. I think that's the entrance chime. Brad is here. Okay.
Yep, that was me.
Okay. All right, Brad. Thanks for letting me know, and we can pop down a couple of slides and check you off is here. Okay. And pop up. Yeah. 313 straightforward statistics. Chapter 14, chi-square tests for goodness of fit and independence. I guess mark this. Some books. Say well, actually type chi-squared. Okay. So most of the books I know from like the 60s through the mid 90s would say chi-squared, and then some of the newer books will say chi-squared. Then some of the really old books from like the 50s backwards would say chi-square, and yeah, same thing, just if there's a D there or not. Actually, a very convenient and powerful thing in many ways. It can be extended in a few different ways, and it's one of the real basic ideas of dealing with tables of values when you have counted observations in the tables. So political party affiliation versus support of a mask mandate. We'll probably guess what that would be, but we'll what that might look like. But you could ask 500 people, and you want to see if there's any difference regarding that. And that's the independence case, to see if those two things are related, whether you have counts or not. And then the other is goodness of fit. And we have sort of this underlying idea that we make an assumption that distribution is normal. We can make a histogram of the data we have, and we could check to see if the histogram fits the normal. But there are simpler cases to see if throwing a die works, or yeah, and we have other tests for that. Flipping a coin, or seeing if your balls in your lotto contest are working correctly. And this is the last week of, if you look at the syllabus of new material. My current thinking is I'll have the exam prepared and let you have a start on that next week. Somebody new here. Brittany's here. Okay.
Yeah, I just got on here. I'm still at work. Sorry.
It's okay. I know, work is hard to manage these days, and have to log in and stuff. Yeah. Life seemed simpler a year ago, at least for me. Although that wasn't the best year for me either. I don't know. I'm thinking back, like 2015, it seemed like a different time. Oh, yeah. Let's see. So we were talking about this chi-squared. So the goodness of fit tells us if our models work, if let us check to see if our histograms meet our theoretical assumptions. And the only things we practically have tables to check are the normal now. And there are other types of distributions that are out there, and you can check it with that. And you can also check to see if someone is cheating in the way they're dealing with cards or something. The likelihood of getting things, and so forth, to see if things fit. So you could check to see if your normal assumption model is right, or if your a die is fair with a goodness of fit test. Isn't that isn't used as much in social sciences as it would be in engineering and business planning tasks. Yeah. So I guess I was saying too, I'm thinking next week I'll have your exam ready, and hopefully your final, and hopefully get a bunch of stuff graded. Life should be getting a little more settled here at my son's house. And yeah, I know many of you've got weird circumstances. The COVID restrictions are difficult on the reservation, and your access to resources are different. And it's um, well, okay. I'm just hearing some conversation um, in my other ear. Yeah, so I'm thinking I'll have that together, and as I'm thinking, I like the idea of doing a comprehensive exam, being you have some time to think things over, and um, we'll and I did see some good results from the way I went over things on the second exam. I'll probably get that graded up and sort of bury myself in grading. Hopefully, we can get you everything that we need. Um, and we did go through the attendance earlier and got most of you, I think. Still looking for Tamara, Christina, Joni, who are often here. Samantha's likely going to show up. uh, I got some interest in she's doing, and Justice usually shows up too. She's not here. Some notes on status. I don't have any stuff. So this is straightforward statistics, and I put my little note also called chi-squared. Oh, got kind of a personal story here about a chi-squared. Um, there's um, a nickname common in Philippine culture and Mexican culture, maybe some others, called Chi-Chi. There used to be a Chi-Chi's um, uh, chain of restaurants, of Mexican restaurants, pretty much across the country, and there was one in Sioux Falls. Um, and we'll see who's chimed in. Brittany, Justice is here. Okay, go back and log in, Justice. Okay. Right. Uh, oh, where are we? Okay. Yeah, about the woman I know. Uh, a nickname as she was growing up was Chi Chi. And Chi, of course, is spelled just like Kai here, and the squared means the two next to each other. So when she was studying at the university, studying statistics at the University of the Philippines, some of her friends called her Chi squared. Okay. I I remember the day I found that out, which is a little strange. And chi-squared here uh, was my um, roommate of my fiance just before we got married. So um, I would have to say that I replaced chi-squared because my wife became my roommate after we got married. So yeah. So in a certain sense, in my wife's mind, I've managed to replace chi-squared. All right. I suppose if I was skillful, I could make that entertaining, but not so entertaining. Yeah, Justice, you just missed avoiding that. What you know, chapter 14 also includes the 4-step hypothesis testing is considered. Other books will have a different number of steps. The book they teach out of in math, science, and technology, or had, is actually uses like 8 or 10 different steps, and it breaks up making the decision into the technical part of the decision and the practical statement, and so forth. So yeah, you can do this for chi-squares. For the chi-square test, you can use the 4-step procedure again, and it's helpful in a way of thinking about this. Okay. Other things that we've done, the tests of correlation, t-tests, regression, are referred to as parametric statistics, meaning we have to assume a particular distribution. With the chi-square and the symbol there, is this, okay? So there's a Greek letter called chi that looks like an X, and when it's raised to a power, it's chi-squared. And it's a non-parametric statistic, which means we really don't have to assume a distribution format. We're just looking for things and don't assume distribution formats. In the t-test, of course, we assume some underlying normals, correlation tests, and regression tests. When we did them, underlying were normal assumptions. And ANOVA, it's a chapter earlier that we've skipped. Worth, everything mentioned in this book. This first book is actually pretty broadly used in some disciplines. Others not so often.
Frank,
Hi, Brad.
yeah, that's like an equation, that X with the square, that's going to mean that that's the symbol for the chi-square,
Yep,
right?
that's it.
Okay.
Yep.
Okay.
That's the symbol for the chi-square. Yeah, it's pronounced with a hard K, chi. Certainly, I realized that, you've seen this, you've only seen this for 20 minutes ago, and not everything floats quickly into people's minds. We don't, we as instructors don't get to write into your head just to tell you things in hope so you remember enough of it to get through it. So,
My boys are watching Kung Fu Panda, so I was saying chi.
oh, they're watching Kung Fu Pandas. Okay. Yeah, I don't think my grandson has anything on right now. Yeah, my son is my grandson is 2.5, and my son and my daughter-in-law are 30. So I kind of miss out on a lot of the. Our household doesn't have a broad interest in children's things, except things for the very young. My grandson really seems to enjoy Blippi, for one. Okay, so chi-squared is based on frequencies, and we use this letter O, which is a little unfortunate because it looks so much like a zero, is observed frequencies. They can only be whole numbers. So overriding this is what we observe. This is the counts that we have, and we can just give that an O. And then E, we use expected frequency. So for some kind of theoretical reason, we calculate a number that's expected. So if we were going to check to see if our die was fair, it would be 1/6 is E. And that's a theoretical reason for it. And that's pretty much the simplest one. I guess if you used a uh, tetrahedron, you could actually make a 4-sided die, or you could make a 5-sided die. Um, um, and then have the expected values 1/4. And then there's this a somewhat practical rule. To make some of the theory work right, you have some regular conditions in it, and this is just, we need to kind of have this set up to get things to work right, and these kinds of rules apply to all kinds of things. If you realize, if you're using an automobile, there has to be a certain amount of air in the tires, and uh, and other kinds of things. You're not supposed to operate on certain kinds of inclines, and uh, um, and there are some rules for this, and it's kind of easy to come up in real data things that are a little sparse. So no more than 20% of the cells in a chi-square test with an expected frequency of less than 5. So that's a rule that there usually is this expected frequency less than 5. Some books will have a little different rule for this. Essentially, we have our cells. We in the problems we look at, we get our O's, but we also have to look at calculating our expected value E's, and they have to work out this way. This is actually a real simple formula for chi-squares. For each cell we have, and it could be, if we were checking to see if dice are fair, counts of 1s and counts of 2s and counts of 3s and so forth, we have an expected number. So if we roll the die 6 times, our expected number of 1s would be 1, right? Because it's 1/6 each. NP, and so forth. And we also have our observations, and we do this little calculation. We take the difference between the observed and the expecteds, we square it and divide it by E. Large discrepancies between the O and the E lead to a large calculated chi-squared. Okay, so if things are very different, we get a chi-squared that's different. And then we can say our expected didn't work out right. We didn't see what we expected. If we have small discrepancies between the O and the E, lead to a small calculated chi-squared. E in a goodness of fit test, in a one-way frequency table or a goodness of fit test, E equals NP. In other words, we have a population proportion or theoretical or assumed stuff, or you have probability theories in chapter 5, and and with the probability theories, we could come up with all kinds of rules for probabilities that we can calculate, and more advanced books would lead you to looking at probabilities for card games in different situations. So you could look at the probability of you being dealt a full house, a poker full house with 7 cards. And see if and you could deal out, shuffle your deck, deal out 7 cards each time and see if you get a full house, and those kinds of calculations exist. And it's also checking to see if your die is fair, is probably just rolling it and noting how many counts are each to see if it's uniform. Have somebody else showing up. Justice, Victoria, Megan, Brittany, Jermaine, Felicia. Oh, I got a little. Samantha's here. Okay. That's pretty easy to recognize with her picture, with the picture she chose there. So we can go back. And do I have a chat? No, I just dragged across it. No. Okay. And just bounce up. All right. And okay. About an hour in, a half hour in. Okay, Samantha, welcome. As if you've been watching your screen, you see I marked you attending, and talked about E is equal to, okay, population proportion or theoretical probability. And yeah, we did a little bit of this in chapter 5, and you can make multiple careers out of calculating probabilities. Yeah, theoretical ones, at least. Oh, probably less than that. And for independence test, rows versus columns in a table, a contingency table, two-way tables, anything you can put your counts in 2 ways. So, a region of the country you're from, likelihood that you've skied, your experience with skiing, never did it, done it a few times, do it regularly, um, and so forth, or some other things. You know, how often you eat fry bread? Uh, um, you know, a few times a year. Never had it. Um, you know, a few times a month, more than a few times a month. You can put that against any other variable that can be um, uh, computed. So we can come up with this kind of table and probably come up with probably do one. Uh, Probably is something that's nice to uh, uh, talk about in class. If you can get things that would break up pretty uh, friendly. Uh, and if I would have given myself a while to think about it, I probably would have come to that. Uh, so we sum our rows and we columns, and we get row totals and column totals in our table, and we get our E with just row total versus column total over N. When we actually go through looking at these kind of problems, it'll be a little easier to describe than just this texty stuff. For each observed frequency in a two-way tape, you can calculate a corresponding expected frequency. Yes, by just using the row totals and column totals. All right. And well, how do we calculate the expected for the independence test? The expected frequency in each cell has the same proportion as the row column and row total and column total relative to the sample size. So essentially, we can use that formula there. Both observed frequencies and expected frequencies add to the same row and row totals and column totals. So both the observed frequencies and expected frequencies add to the same row and column totals. We can use this to check something. All right. So somebody want to type out a chat answer. We go through this process. Okay. We have our observed frequencies, and then we can get our row and column totals from that. After we get the row and column totals, we can then compute the expectant frequencies with this formula on the page here. Okay. Then we have this property that the observed frequencies are original table and our expected frequencies add to the same number of row totals and column totals. Can we use this to check something? And what would that be? Or maybe I just been talking too fast. So wait a while, see if somebody speaks up or gives me a chat message on that. Okay. All right. Yeah, maybe I just been talking too fast or not drawn enough. I used to check what? I used to check calculation of expected values. Okay. Yeah, the critical values of chi-squares identify the values that set the boundaries of their rejection zones. Okay, so we have critical values, we have a chi-square table. The degrees of freedom in the chi-squared goodness of fit test is C-1, where C is the number of columns or categories in the one-way frequency table. Some books will give you a little more general discussion of that and have a slightly different response. So to find the rejection zone, we calculate the chi-squared, and then there's a chi-squared in the table that we look at. So this is the number we calculate, and this is the number we look up for critical regions in a tabled value. Okay, so if your calculated is greater than your tabled, you reject the idea that that your original goodness fit worked. So chi-squared numbers here can only be positive. When we look at the formula, we can see why. Here, this number is squared, although it's a difference. It's squared, so that's a positive number. E is a positive number. And when we add them all up, we'll get a positive number. Right. Now, the 4-step procedure on the chi-squared goodness of test, fit test. We'll go through one of these problems and from the book, and this time I leave a lot of the calculations in. Well, I do a few of them for you. Do want to take some care for this, and let's so the 4 steps: state the pair of hypotheses, identify a rejection zone, calculate the test statistic, draw the conclusion. So state for the one-way frequency tables or the goodness of fit tests, we state it this way. So we're not describing any population parameters in a strict sense. We just have a particular variable fits a theoretical distribution. Okay. You can check uniforms or binomials, and if you make some adjustments, normals and other distributions by checking a sort of a histogram to see if it works right. We can check to see if our histograms meet our theoretical values. or if it's a pure counts data like a binomial or a discrete uniform, we can do that also. And so our null hypothesis, which is our common or usual status, and then our unusual or strange or research hypothesis is it doesn't fit the theoretical distribution. So in this sense, we're looking to prove our die isn't fair. Most of the time, people try to build reasonably fair dies. But it is possible that you can cheat. If you were, playing around with some manufacturing operation, you could build yourself a die which is not fair, moderately easily. If you had like a 3D printer, it would be fairly easy to build a die with a cavity inside. Um, that would be extremely biased, unfair. The critical values of chi-squared are in Appendix H in the textbook, and see if they have if we got the number right in the slides. Critical values of chi-square tests is Appendix H, and it's on. I guess I might. Yeah, I don't know how pages 509 and 510. You need an alpha level and a degrees of freedom to identify the rejection zone. So somebody needs to give you an alpha level, and you have to have degrees of freedom. And it's C minus 1. What did we have? Defreeze is C minus 1, where C is a number of columns or categories. So you look up an alpha level, you look up a C minus 1, and there's your rejection zone. So that's the procedure. Critical value of chi-square tables. They gave me these slides, and looks a bit like this. The numbers are all the same as in the textbook for the first 4 values of degrees of freedom, and they go down to 9. So then calculate calculate this: observed minus expected squared divided by E. Seems like we've gone a long time without doing a calculation here. Make the correct conclusion. If the chi-squared is in the rejection zone, we reject it in H naught, and we assume our model doesn't work. If chi-squared is not within the rejection zone, we reject H. We fail to reject H naught, so we haven't shown it this way. So, you suspect a die has been tampered with. Okay, someone's playing. I don't know how I can tamper with a die. I know, maybe shave a corner or something, or an edge. Yeah, I guess if you shaved an edge, it would be more likely to roll over that edge than to uh, I'll take less energy to turn on that edge, and therefore create a different likelihood of the numbers that comes up. Or I suppose dies have dots that are filled up in various ways, the dots on the die, and if you used a very heavy material in those dots or dug deeper in those. I have not looked into this very seriously. Conduct a hypothesis test to see if this die is fair. So you roll it 36 times. So this is a poor choice, X. So this is numbers we can get on the die: a 1, a 2, a 3, a 4, or a 5 or a 6. So grab a die, look up what's on the sides, and you'll see the numbers 1 through 6, usually. Common game board die. I guess there are some gambling games that are played just with dice. I'm not a gambler. I do show up in board games as random number generators pretty often. Your observed values, and these will add up to 36 because we said it's 36. So we might want to go through here and see if they do add up. 9 plus 5 is 14. 14 plus 7 is 21. 21 plus 4 is 25. 25 plus 3 is 28. 28 plus 8 is 36. Yes, so we do have 36. And we have then E. Our expected value is 6. Okay, so 1/6 of the time. So we'll get a 1, a 2, 3, 4, or 5 if we have a fair die. Those are the expected numbers, the average values that we have, and they're all 6s across the board here. Now we do this calculation. So step 1, the die is fair, all right? So our 1/6 is 1/6 of the time it'll come up with the numbers 1 through 6. Our assumed usual state, null hypothesis, H0, die is fair. H1, the die is not fair. 0.1 degrees of freedom is, and it's a minus sign here, and I guess this actually should be equal sign. So number of categories, there are six sides to the die. 6 minus 1 is equal to 5. The rejection zone is equal to chi-squared. So the rejection zone, the number we look up from the table is this 11.107. And with alpha is equal to 0.05. We have the tables back a few slides. Alpha is equal to 0.05. Degrees of freedom is equal to 5. Let's see if we get that same number. This is degrees of freedom is equal to 5, and alpha is equal to 0.05. So the second one, we're considering 11.07 there. Okay. I guess I can escape out of this. Yes. And I can pull up, I'm sharing the screen. The chi-square table in the back of your book looks a little more like this. And the way I usually, degrees of freedom is equal to 5, this row. Alpha is equal to 0.05. So this column, and this number is what we get, 11.07. So that works out. And from current slide might be the best. So we go through and we get our 11.07. Wow, where am I? Did I click up too far? And then we add up, we sum up all the values, all of our observed minus all of our expected values. So this 9, this 5, this 7, this 4, this 3, and this 8 are all our observed values. So they come from this table here. Observe 9, 5, 7, 4, 3, 8. And they each have their own term here of this difference squared divided by the expected. So it's 9, 5, 7, 4, 3, 8 is the same as that row of the O's. Okay, so these are all O's. And then the E's going to be the same each. And because it's a uniform, they're always the same. So 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, E. Right? When we do all those calculations, and what we'd have to do here is we'd have to calculate this difference and square it, divide by 6. Calculate this difference, square it, divide by 6. Calculate the difference, square it, divide by 6. Calculate the difference, square it, divide by 6. We get 4.67. 4.67 is not in the rejection zone because it is not greater than 11.07, so it's smaller than that. So we fail to reject it, and we say this die, we can't claim that the die is not fair now. So this is just 36 throws. If we did 36,000 throws, we might notice a difference, that the die might not be fair, but you know, the differences might not be enough to change a strategy in a game, for example, or realize that your that you know the nature of your game. You want to put this, put all the equipment in the box for under $5 or something, and maybe you only take a certain amount of care with how fair your dice are. I guess if we were in a classroom, we can have people, roll some dice, check that out. Oh, there. There is a way to come up. You can do things with coin flips too, and you can come up with a biased coin. Do that. Yeah, be worth the trouble. A test of independence. This is when we look at the table. Two variables are independent of each other. The two variables are not independent of each other. So one would be helpful in predicting the other. And our degrees of freedom is R minus 1, where R is, yeah, we didn't state this. Here, probably should. R, number of rows. And C, number of columns. So the rejection zone for a chi-squared independence test is identified as chi-squared is greater than chi versus, and this time we have our degrees of freedom calculated, R minus 1 times C minus 1. So a little bit more of a calculation. So our simplest table, a 2 by 2 table, it's 2 minus 1 times 2 minus 1 is 1. So that's one of the easier kinds of questions to do. So calculate the chi-squared. Step 2 is then calculate the chi-squared statistics, where E is row total times column total over N. Make the correct conclusion. If the calculated chi-squared these are out of order. So you have to switch the order of these to read it correctly. So if the calculated chi-squared is within the rejection zone, we reject H naught. If the calculated chi-squared is not within the rejection zone, we fail to reject. So these are out of order in this slide, and I didn't read it as carefully as I should. Okay. Chi-square test for independence. A company specializing in medical devices underwent workforce reduction for its sales force. Okay. Workforce reduction, furloughs or layoffs, huh? Likely layoffs, okay? The outcome of a workforce reduction for an individual employee can be classified as either laid off or not laid off. Okay. So the employee's gender can be classified either as male or female. Yeah, most of the statistics books are written a few years ago, and we don't have the less common genders are not often given in the standings where you could, possibly have intersect or transitioning, are not included here. Although it may well be possible to get 100 people that are neither um, um, intersect, uh, intersexual, or in transition, or non-binary. So laid off, 30 people laid off, 70 people are not laid off. These are the column totals. And then the row totals are, and so that might have been a planned thing to go down there. And then male, not laid off, and female not laid off. And we have then totals male and female, 33 males and 67 female. And we want to see if these numbers, if there was bias in the layoffs based on this table alone. Of course, in layoff procedures, there are other things. So if you were going to go to court and say there was a gender bias in the layoffs, you'd at least want to make sure that your chi-square test indicated that this wasn't just random. Now the company could go back and look at other things like rank sales based on actual sales versus their target values, and it could well be that they just lined up for employees their procedure, which was percent of target value, and just cut them at one point or something. And if they went to court, they could bring that forward and say, that's how they did it, and they weren't biased in any way. But if this chi-square chi-square table didn't pan out, then you probably wasn't significantly different, didn't show that there was independence here, you'd kind of be done and go into court over this. So let's see if a layoff decision employees gender are independent. It should be noted that this is actually the kind of problems and consulting that the author of the textbook does, is, a side gig besides for professor work. So state the pair of hypothesis, layoff decision and employees gender are independent. So layoff decision and employees gender are not independent. So it's a very small table. So our 2 rows and 2 columns. So we have 1. So, and alpha is equal to 0.05. So the rejection is chi-squared is greater than. Okay, and I think that was leave chime, return chime. See if I can see a new name there. I don't recognize the new name there. Okay. I think that might have been a leave chime. Somebody just popped in and out.
Oh, that was me. Sorry. I just switched from my phone to my laptop.
It's okay. That's fine. I no problem. I realize people have it's a difficult circumstance, and it's not as easy for all of us as just walking in a classroom and walking out. Calculate the test statistic, row total versus column total, and so where do we get these numbers? Row column versus column total. How do we get one of them at least? 9.9. All of a sudden it shows up. Let's at least get this 9.9 number and show you where it comes from. Row column total versus column total divided by n. So this one then is 30 times 33, the column total, row total, divided by 100. So this is a fairly easy calculation. So this was, the numbers were the numbers were 33 times 30 divided by 100. And this was, this is n. And this is the row total. And this is the column total. There's the equal sign there. So 33 times 30 would be 990. 990 divided by 100 is 9.9, and we get a calculation there. And the appropriate rows and column totals. So this one, row total is 33 times, and our column total was 70 for this. So this is our row total because we're in the same row. And our column total is 70 and 33. Well, 3 times 70 would be um, um, uh, 3 times 70 would be 210, and then 30 times 70 would be 2010, and we add them together, we'll get 2310, and then we divide by 100 our grand total, our same end, we'll get 23.1. We go back and look at our tables. Yes, that's a 70. And this is a 33, our row total. So same row totals in the same row, same column totals in the same row. And now we're in the same column here, same column total. So this is 30, but this time our row will get 67. And divide by 100, and 67 times 30, like just about works out to be just about 2/3. So we multiply it out, we'll get 20.1 divided by 100, and then finally we know our rows and we know our column totals from previous things. So 67 times 70 is equal to 100, and this then, does that seem to work? Yeah, well, 70 times 70 would be 400, would be 49.0. Yeah, I have to pull out a calculator to verify it, but it looks pretty reasonable. Now, we did mention one way to check your work is to see if the row and column totals add up. So 9.9 plus 20.1 adds up to 30. So we can have totals here. And we can then have a total of 30 here. Looks kind of like a 36. And we can then have totals here. The 23.1 and the 46.7 add up to 70, our column total. And if we wanted this, our calculations check here, so we're going through that calculation check. And then the 23.9 and the 23.1 and the 9.9 add up to 33. And I guess if we put totals here and 67, yeah, that adds up to 67. And our grand total ends up being 100. So it's pretty easy to get your miss a calculation here or there in a table like this. So you do want to go back and recalculate your totals. And if your totals if you have just like one number wrong in your calculation, the the particular row will have the wrong total, and the particular column will have the wrong total. Oh, so that tells you you have just one number wrong. So, well, and in other words, they can be compared with the row column numbers here and tell you just where you made your mistake. So that's a real easy kind of thing to do that. So we have our four numbers in two tables, and these were our observed numbers. These are our expected numbers that we calculated. And when we go through this whole calculation, we get 5.7. 1, and our rejection zone is 3.841. So strong evidence to support the gender and layoff decision are not independent. So you could see if there's might want to take the company to court over this, at least on this table. You might want to meet with the company to see if they have another explanation. And it could well be that they used other things. So under the assumption of layoff decisions are independent of, so we can then say the company appears to be unjust in its work. Go back a little, look at the actual totals. We had 25, 28, 42. And let's see, I can escape the slideshow, escape. Do I want to save my annotations? Keep, and get out of that. And I have Excel. And is Excel, let's just add a new sheet. And was it 525 525 28 42. Okay. Yeah, does that add up to 130 and 70? Yeah. Okay. View, zoom, 200%. That was our raw data. And if we include the data in there, what do we have? Drag those things out of the way. Data. Go to data analysis. In data analysis, do we have it there? Z-test. Regression sampling. No. I thought there was one. Yeah. So there isn't a chi-square test in that, but you know, we do have in Excel home, we do have auto sums. And we can do our sums quickly. Just drag them down, and we can go through in home and auto sum. And get our sums quickly if we were just given raw data. Drag them over and so forth. And then, you could we can actually get an auto sum, and it sums a column as a default, and that does work. You can build a expected table here. With oh, no, that's not what I want. An expected value. This times this, and we then could could anchor the row here and enter and drag this across and see, and then you copy this down. Are we okay? No. And do a similar calculation, and then could divide the whole thing by 100. In other words, we could use Excel. And I've messed this whole thing up, haven't I? We could use Excel in our patterns to make use of this, but it would take some building up. So it isn't a default technique in Excel. However, you could use this to do your calculations and set up your tables and so forth. So it is a little, it can be useful. There are packages that will do this chi-square test automatically. However, I had thought that it was in Excel. I'm sorry about that. And I'd probably just as well remove the sheet. Can I click on this sheet? No. I'd do something with that sheet. No, I got a problem with this. Why don't I just clear that off, enter, and get something that's useful? And now will it let me remove the sheet? Rename, insert, move, copy. Delete. Yeah. Yeah. So I was just playing around with that. Okay. Yeah, somehow, for some reason, I thought that there was a chi-square test in Excel. I might have got confused. So we went through this in this table. Might be helpful to identify each of these numbers. These are the E's. So these are all the numbers in our E table, and they show up. And that was our calculated values here. And our O's came from our original data table. And we get our 5.71. And we compare it to our 3.841. And it appears so it does appear that there may be some bias in there. So if someone was coming to you looking for some help to see if there was gender bias in the layoffs, and possibly to file a lawsuit or 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 something like that, at least at this step, it would look good. What you would do is, well, you talk to. This would be like a first step calculation you do in deciding whether there was bias or not. And it isn't just layoffs where things are there. Men and male employees were promoted, and among them, 7,000 were promoted. Conduct a 4-step hike. So what we have here is we're given column totals, the male column and the female column, and when we have to subtract off to get the table. And sometimes this is just how things are reported. Promotion, the null hypothesis, promotion decision, employees gender are independent, and that they're not independent. So again, we'll use an alpha is equal to 0.05, degrees of freedom is equal to 1, rejection zone is chi-squared greater than 3.81. Number looks a little familiar, right? Well, degrees of freedom are 1 again. That's that. Now, notice we were given this number, the row total, and this number, the number promoted, and we have to subtract to get this. And we were given this number here and this number here. We have to subtract to get this. And then, well, finally, we weren't given this number. We have to add them up, and then we get 6,000 employees. Fairly large organization that has 6,000 employees in one region, at least being here in Rapid. I don't think we have any employers that large. I don't know how many people work at the base or the hospital, but those are the 2 largest ones. So we have our table like we had before. This time the numbers won't work out quite so easily, but they'll fall together the same way. Same example. So promoted, not promoted. Whoa. Our expected table just pops up. My. Didn't expect to see all that. Have to wonder where should it be worthwhile just noting what the calculations were here. rows times columns times, and then divided by. So each of these terms will have okay, somebody went out and came back in. It's the same person, maybe. Okay. I suppose I could look, see if I see a new name.
Sorry, that was me again.
Okay, all right, no problem. Okay, so there were 6,000 in total. So our calculations on each of these, we're going to divide by 6,000. So we know that. We can fill in all these numbers and see if they seem to make sense. Our expected value table. So where did these all come from? So male promoted, the male and the promoted column and the male row totals are what we're looking for this one. So 1660 and 3300. So we have those. 1660 and 3300. All right. So our promoted was 3300. So that's also going to show up here. Those were 33s. Yeah. And no, 3,300 is our row total, not our column. So it won't show up there. That was wrong. And is it control? So this was a mistake here. Okay. So our promoted column number was, our promoted column was the 1,660. So 1660 we know, but our same number of males are going to be in both, so we'll have the 3,300 number here. And let's see, our number of females then will be the 2,700, right? Because we have 6,000 total. Yeah, 2,700. And then our number not promoted column total, we can look up uh, 4,340. All right. And that's where all those numbers came from. And you could pull out a calculator and see. Um, all right. Let's see if I see a new name. No. No, I don't see anything. Okay. Right. And makes a few comments. So our E's show up twice and they're in this table, are calculated. Oh, chat. Who's here? Okay. I got a private message about somebody cutting out early. It's fine. We know. You know, we somehow have the idea of college education setting as relatively wealthy people send relatively young adults off to live in a dorm, and they have nothing to do but keep up with their classes and their social lives, and are fed in adjoining buildings. But life doesn't work out for that's so atypical of the OLC student. Uh, um, so many of you have so many multiple responsibilities, and I know what those all are. So, okay. So the E's show up twice, right? E, 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 E. Oh, and we also want to check to see if our totals work out right. So when we add these two numbers together, do we get the 1660? Yes, we do. When we add these two numbers together, do we get 4,340? Yes, we do. When we add these two numbers together, do we get to 3,300? Yes, we do. When we add these two numbers together, uh, do we get 2,700? Yes, we do. So we can just check those totals again um, explicitly, and we get the O's from our original table, and those O values are here: 96, 700, 2,300, 2,000. So 96, 28.4, 700, 2,000. And go through and so subtract, multiply it times itself, square it, divide by the number, and go through that. When you go through this, is now how good you are with your calculator. You probably do not want to. You have to be pretty good with your calculator to go through this all in one step, right? So you would probably go through this in maybe 3 lines. You can make this subtraction and square it and probably come up with a reasonable number. But some people who aren't real familiar with if they've got a calculator they're not familiar with, just make the subtraction, write it down, and then square it, and then divide, and then do the addition steps. and we got 7.43. And woe and behold, we reject it. So it's in the rejection zone. So the evidence is strong to claim that the promotion decision and genders are not independent. The probability of obtaining such observed values is 0.05. And we might want to look at our tables and see, gee, this 0.05 was kind of arbitrary, and this seems like a pretty big number. Maybe we could even claim a higher number. It's not a proper procedural thing to do, but if you're trying to make an argument with it. So let's escape this, and keep. And we can look at our table and 1 degree of freedom. And we got a 7 this time. So what? 7 point, what was it? I guess I want to minimize that. 7.433. Yeah, so it's actually, we could have rejected even if we set it at 0.01. And in fact, it's pretty close to 0.005%. So it's a 1 in 100 chance, maybe bordering on, getting close to 1 in 200 chance of working through these numbers. And let's see, the command you see, just click on this, show you, actually has the chi-squared functions, are some of the tabled functions in Excel. So we could get p-value there, for example. Yeah. So so this is pretty strong evidence that those layoffs have somewhat a gender biased effect. Is this real data? Well, some of the numbers seem to be a little bit rounded for calculation convenience in both cases. But these are the kinds of problems our author, Che-Chen Bowen, deals with in her consulting work to the community. And yeah, sometimes when you're looking to do this kind of work, yeah, it's the kind of work you kind of need with another job, right? Because people who are getting laid off don't always appreciate that there's they can get this kind of situation. And so where are we now? I did the attendance. I haven't done the tech check in in a while. We did references about what we know. Yeah, this is another hypothesis test. It's a different problem. It's chi-square or chi-squared, and it's a concept here that we can have theoretical values and check to see if the counts work out right, and get that to work. And then also when we have two-way tables, we can check to see if the variables are independent. So we went through the goodness of fit test, the chi-squared test, and talked through this. And then hypothesis testing with the goodness of fit test. Yeah, we checked to see it with 36 rolls of a die, if it was fair or not. we looked at a chi-squared table and showed you the table in the textbook. We calculated a chi-square value and stated a conclusion. We verified the chi-square goodness of fit test. So this is all long theoretical discussion. And then we discussed the chi-square test of independence and ran through 2 examples. Both of the examples were from the textbook, and they dealt with bias based on gender cases, which is what Che-Chen Bowen had done. Also talked about next week getting getting an exam ready, and I have been pretty much behind on the grading this semester. I have started grading the second exam. I do have the results of the first exam that are, I guess I can stop to share and talk to you face to face, but yeah, I just just a setup for grading, and finding a place to mark a table and work and so forth. And here at my son's house in Colorado, we'll and it's just playing a little harder to grade you have a harder time preparing the electronic forms than you do the paper submissions, and on the other side I have a harder time marking the electronic than the paper. And the semester's been a little rough in a lot of ways. But I did get to marking up a few of those second exams, and I do have the first exam results available on Gensbar, and I guess it might be appropriate next week to maybe take a little time to show you how those results could be found. Some of you have had courses where results were back in Gensbar. Well, we could do that. And maybe I could, let's see, pop up, see, let's see if I can log in and it's bouncing around Gensbar now, and okay. All right. Yeah, I could show you where to find those. Okay. Just bouncing. The faculty view is different than the student view, and um, um, yeah, I could probably for you around there a bit. Yeah, I just wasn't prepared to do that at the moment. Okay. Well, I guess I'm letting you out about a half hour early or so for this week. I can stop the recording now, and I'll stop the recording now and ask if anybody's got hang around to see if anybody's got some questions.